Part 1 of the architectural overview was all about the hardware and the functionality of the IoTT Stick and various function heads. In this video I am explaining the communication concepts built into the IoTT Stick, and let me tell you, that is the real exciting part. Welcome to the IoTT channel, I am Hans Tenner. A special welcome to all new subscribers and welcome back to everyone else. I am happy you made it here. The IoTT Stick has three groups of communication functions. First, it acts as web server for the various pages designed to configure and operate the IoTT Stick. Then it can receive DCC track information from the layout, process it to a function head and also broadcast it to other receivers. And third, it acts as a node in a Loconet layout control network, can receive information, process it and distribute the results. Let's have a closer look into these functions, what they do and how they work. The web server provides the user interface to the IoTT Stick. After the initial setup, either as a node in the available Wi-Fi network or as access point without external connection to a network if you prefer, you can point a web browser on the smartphone or the desktop computer and load the IP address that is shown on the display of the IoTT Stick. This will automatically load the main configuration page in your browser. Now you can set the command source and the head type, click Save and Restart, and the stick will then show the additional tabs with selectable configuration pages based on your selection. Some of these configuration screens are simple static configuration pages that load all the data when you open the page and write all the changes back to the IoTT Stick once you click Save and Restart. Some other pages also provide dynamic runtime data and even user input that manipulates some settings in real time. One of these examples is the button setup page of the yellow hat that shows the input status of each input line as you change the input level, and this gives you instant confirmation that you are working on the right input channel. Another example is the setup of the minimum and maximum servo angles of the green hat, where you can use a slider to move each servo to the end position you want for your application. A third example is the amp meter display of the red hat, which can display the track current on both outputs of a DCCX command station in real time. From a technological point of view, if you are interested in that, all configuration pages are written using HTML, CSS and JavaScript for the static part, as well as AJAX calls and WebSocket communication for the runtime data. The DCC functionality is straightforward. The IoTT Stick can receive DCC commands, process them in the function head, and optionally forward them to other nodes via Wi-Fi. To receive DCC commands, the stick implements two methods. The first is connecting the IoTT Stick to the track using a DCC interface and decode the commands in real time. After decoding, the incoming commands are displayed in the DCC viewer, which is automatically available whenever DCC commands are received. The screen is split in two sections. On the left-hand side, it shows the refreshed commands. Those are the commands for locomotives which are continuously sent out by the command station. They contain speed, direction and function statuses for each address in the refresh buffer. If a parameter value of a locomotive address changes, for example the speed increases, the line for that locomotive is simply updated with the new value, but the screen does not display the several hundred commands that are sent over the track every second. On the right-hand side are the commands that are sent out as needed, so turnout and signal commands. Whenever a new command from this group is decoded, a new line is added to the display for that command. And by the way, you don't need a terminal to see the decoded commands. If you rotate through the screens on the stick display, you will see them on the built-in DCC viewer, and you can use the stick button to toggle between refreshed and one-time commands. If you want to send the decoded commands to other nodes, you can activate the MQTT broker gateway. You then open the MQTT broker tab to specify the broker to be used. You can use a private broker running in your network or a public broker somewhere on the internet. In the lower part, you can set a node name and specify the broadcast topic you want to use for this broadcast. That's all. The incoming DCC commands are now automatically uploaded to the MQTT broker, from where an unlimited number of other nodes can get them. For more on this, watch video number 56, where I showed how to use this method to build a DCC viewer running on a smartphone web page. To connect another IoTT stick to the broker and receive the DCC commands from there, all you need to do is setting the command source of that stick to DCC from MQTT. After saving the settings, the IoTT stick will display the MQTT client page, where you can define the broker you want to receive the commands from, and again the DCC broadcast topic. These two settings match the receiving stick to the broker and the commands broadcasted by the first stick. Open the DCC viewer on the second stick and you will see the same commands coming through like on the first IoTT stick, maybe with a few tenths of a second latency depending on the location of the broker you selected. To build a DCC command distribution network, you set one stick as broker gateway and several others as DCC clients. They will all receive the DCC commands and can use them to set output functions like turnouts or LEDs. And you can go beyond that. Even if a stick receives the commands from a broker, you can still make it work as broker gateway on its own, either with the same or with a different broker. Just make sure you are using a different broadcast topic for each new broker connection. And if you choose a broker service on the internet, you can easily distribute your DCC commands over the entire globe, and setting a turnout position on your layout at the same time could activate a relay in another country or even on a different continent if you want. Now, if this already provides a lot of flexibility, there is even more you can do when using Loconet Communication. The main difference, of course, is that Loconet is a layout control network, which means it is bidirectional and messages can flow in both directions, other than DCC, where all information comes via track from the command station. What makes Loconet the control network of choice is that it has everything needed for layout control, is reliable, has very little administration overhead, but still is an event-based peer-to-peer network. If you are not familiar with these terms and would like to know more about how Loconet is different and, in my opinion, better than layout control buses like the Lens ExpressNet or the NCE CAT bus, I recommend watching video number 59, where I explain the key differences in some more detail. Like with DCC, the connection to Loconet can be wired or wireless. The wired connection requires a Loconet interface port, which connects to the growth port of the IoTT stick. In the setup, you then choose Loconet interface as command source, and your stick is connected. On the web page, you get a Loconet viewer tab, where you can see the Loconet messages flow, and to understand them better, you can have them translated to plain English. The stick has a built-in Loconet decoder and can process Loconet messages to set output functions on a function hat, for example LEDs on the blue or yellow hat, or servos on the green hat. But other than with DCC, the IoTT stick now can also send messages back to the network. For example, when using the yellow hat, it can send input information from the 32 input lines either as button messages, turnout position messages, block detector messages, or even analog values. Those messages are broadcasted over Loconet and can be used by any other node to trigger actions or calculate, for example, a signal status of an ABS system, and much more. This does not only work when connected via Loconet cable, but also wirelessly. For that, the IoTT Stick supports several communication protocols that can be used. The first is Loconet over TCP, which is a client-server protocol developed by Stefan Bormann in Germany about 20 years ago, and in the meantime is supported by many command stations and model railroad control softwares. Maintaining the tree structure of Loconet, the server connects to the Loconet that originates from the command station, and the clients then connect into the server. If a command station supports Loconet over TCP, it usually provides a server. Software like JMRI has typically both a server and a client, so it is possible to interface to the wired Loconet and provide a Loconet over TCP server, and on the other hand, JMRI can also connect to a Loconet over TCP server on a different machine using the built-in Loconet over TCP client. On the IoTT Stick, Loconet over TCP works the same way. The stick can operate as a client connecting to an upstream server, and it can provide a server for other clients to hook into. It is even possible to have both on the same stick at the same time, so getting the Loconet messages as client from a server, and then provide a Loconet over TCP server so that other programs or IoTT sticks can hook into. Here are some examples what you can do. JMRI is connected with a locobuffer USB to Loconet. You can activate the Loconet over TCP server in JMRI and connect one or several IoTT sticks with function heads to it. For example, a blue hat with an LED chain for signals, a green hat with 16-channel servo decoder for turnouts, a yellow hat to connect up to 32 block detectors wirelessly to Loconet. Or you can use a Loconet interface with an IoTT stick and activate the Loconet over TCP server on the stick. Now you can connect additional IoTT sticks like in the previous example, but this time they connect directly to the Loconet over TCP server on the IoTT stick. If you want, you can still add a computer with JMRI, but this time you can connect JMRI as Loconet over TCP client to the IoTT stick. By the way, the Loconet over TCP implementation on the IoTT stick has one major advantage compared to the one in JMRI. If the Loconet over TCP server shuts down, the IoTT stick clients will automatically reconnect when the server comes up again. This is unfortunately not the case with JMRI. You have to restart the software if that happens. The second option to connect IoTT sticks using Loconet is connecting them to an MQTT broker, similar as it is the case with DCC. The node that bridges between the upstream Loconet and the broker is called the MQTT gateway. It can be connected to Loconet using a Loconet interface, or as Loconet over TCP client, or it can receive the commands from another MQTT broker. Either method works, but you need to make sure to maintain the tree structure and not accidentally create a loop where messages could go round and round forever. Next, you check the MQTT gateway checkbox, and on the MQTT broker page you specify the broker IP address and the broadcast topic you want to use. The IoTT stick will now connect to the broker, and your Loconet messages become available for a multitude of other nodes that connect to the same broker using the same broadcast topic. Like with DCC, you can use a private broker inside your network, or you can send the messages to a public broker on the internet. Furthermore, the IoTT stick can also receive commands from an MQTT broker. For that, you select Loconet from MQTT as command source, and then use the MQTT client tab to select the broker and to set the Loconet broadcast topic to the same you entered in the MQTT broker configuration of the broker you want to receive the messages from. Also here, it is possible to define several virtual Loconet branches using different topics, even if they run on the same broker. Using a separate topic is enough to separate the individual branches. Maybe you wonder why the IoTT stick is only using a single broadcast topic, while MQTT implementations like the one in JMRI use separate topics for switches, signals, feedback sensors, etc. The reason is that on the IoTT stick I implemented a Loconet over MQTT message structure that sends complete Loconet messages just encoded into a MQTT format. That way, each node gets all messages like in the real Loconet. There is really no point for using different topics for turnouts and block detectors if the distinction is already included in the Loconet message itself. Splitting it into separate topics, therefore, is somewhat artificial in my opinion, and it makes the administration of the system ways more complex, as I explained back in video number 49 in some greater detail. The third server that is available on the IoTT stick when using Loconet is the WiThrottle Server. This is a protocol developed by Matt Hoffman to control locomotives and turnouts from a smartphone or tablet. Several smartphones can be connected as clients to a server, and currently there are two apps I know about that support it: WiThrottle for iOS and Engine Driver for Android. Both apps can be downloaded and installed from the respective app store. On the IoTT stick I implemented a WiThrottle server that communicates with Loconet and can control locomotives and turnouts, and also supports some other functions of the command control system. To make the IoTT stick a WiThrottle server, all you need to do is checking the WiThrottle checkbox. And of course, the IoTT stick needs to be connected to a Loconet, either using a Loconet interface to a wired Loconet, or connecting as Loconet over TCP client, or getting the commands using the Loconet from MQTT option. You can connect several smartphones to the same WiThrottle server, and you can have as many IoTT sticks as you want connecting to the same Loconet and running individual WiThrottle servers. And just in case you wonder, the IoTT stick also has an onboard WiThrottle client, so that it can connect to a WiThrottle server running on another IoTT stick or to the WiThrottle server of JMRI. This connection can currently be used by the Purple Hat when running an automated speed calibration process. At this time, the Purple Hat is the only function hat that can control speed and direction of a locomotive, but this may change in the future. Now, what really adds to the flexibility of the IoTT stick is that those three server functions are not mutually exclusive. In fact, they can be used in any combination simultaneously. So one single IoTT stick can serve as Loconet over TCP server, MQTT broker gateway, and WiThrottle server all at the same time. One last thing to think about is whether to connect the stick to an existing Wi-Fi or configuring it as access point on its own. In general, I recommend connecting the IoTT stick to an existing Wi-Fi network router. The reason is that an access point needs to manage the connection statuses of the connected nodes, which requires computing power and memory. So the number of simultaneous connections on an IoTT stick is limited. If other sticks and smartphones connect to a router instead, the management function is provided by the router, which typically can handle many more client nodes than the IoTT stick. If you don't like the idea that your model railroad is connected to the internet, you can always use a router that is not connected to a modem or router. Therefore, is not connected to the internet but only provides a local Wi-Fi without external connections or access possibilities. This is certainly preferable over using the IoTT stick as access point. And that's it for this video. I hope this information was useful or at least interesting for you, and you have a better idea now how the IoTT stick can communicate with your command control system and help to set up a local or even worldwide control system to operate your trains. If so, please click the like button below to let me know, or leave me a comment in the comment section of this video. I really like to hear from my viewers, and all feedback also supports the IoTT channel as it motivates YouTube to suggest this video to other model railroaders. Thanks for watching and see you in the next video.